So hello students, our today's reaction is, it is Williamson's synthesis. One of the most important method for preparation of ethers, and one of the major advantage with this reaction is that by Williamson's synthesis we can obtain symmetrical as well as unsymmetrical ethers. See, in Williamson's synthesis what happens here, alkyl halide are treated with sodium alkoxide, and as a result here we get ether along with sodium halide. See, this ether, it may be symmetrical as well as unsymmetrical, depending upon our requirement. We may prepare symmetrical as well as unsymmetrical here. The generalized reaction can be written as, see, this one is alkyl halide, and when it is treated with sodium alkoxide, this Na comes out with the X, and you will get here RO R dash plus NaX. This one is ether. As the two alkyl group linked over ethanol oxygen both are different, one is R, one is R dash, so it is example of unsymmetrical ether. This is sodium alkoxide and this one is alkyl halide. Now thereafter we'll discuss that what's the mechanism, how the reaction occurs. So we'll discuss its mechanism. See, in this reaction this alkyl group is being replaced by the alkoxide ion. Means here, as in alkyl halide there is a polarity. This alkyl part bears slight positive charge and X part bears slight negative charge. Polarity is here. So here the X minus is replaced by the alkoxide ion, which acts as a nucleophile. This one is acting as nucleophile. So here nucleophile is replacing this group. It is a leaving group. So therefore the reaction is example of the nucleophilic substitution reaction. See, and as you know, in nucleophilic substitution there are two mechanisms. So this part in Williamson's synthesis, the reaction occurs here. This reaction occurs by SN2 mechanism. In SN2 mechanism, the nucleophile approaches or attacks the substrate molecule from the trans side to the leaving group. Our reaction is, it is CH3 CH2O Na, this is sodium ethoxide, and here it is CH3 Br, it is methyl bromide. So how the reaction will occur here? See, this is CH3Br, and this one will be attacked by this sodium ethoxide dissociates and produces sodium ion along with ethoxide ion. Now, this ethoxide ion, which itself acts as a nucleophile, this will attack from the trans side to the group which is to replaced. Means here Br is to replace, so the group Br is called here a leaving group. So in SN2 mechanism, the nucleophile this nucleophile attacks from trans side to the leaving group. In this case, our leaving group is Br, so this ethoxide ion will attack from the trans side, and here you will get a intermediate in which a bond between oxygen and carbon is not completely formed, and the bond between carbon and leaving group Br is not completely broken. So this type of unstable or intermediate state will be formed here. This one is called transition state, and thereafter the carbon bromine bond breaking occurs. This Br minus will come out with the Na plus in the form of NaBr, and here a bond between oxygen and carbon formation will occur here, and in this case there will be an inversion in configuration occurs. So this one is the mechanism for the Williamson's synthesis. But the Williamson synthesis are having certain limitations, and the limitations are so here we are going to discuss the certain limitations of Williamson synthesis. The first limitation is while we are making some mixed ethers, formation during mixed ether formation, suppose our mixed ether is CH3C, CH3, CH3O, and here it is CH2, CH3. This one is our mixed ether, and now this ether is to prepare through the Williamson's synthesis. So here the ether can be obtained by taking these two as a reactant. Here I am taking a primary alkyl halide. See here, an ABr will set free and you will get the desired product. The another option is we may have tertiary alkyl halide as one of the reactant, and then this NABr will set free and we may get our desired product. So the limitation is, while making this type of mixed ether, so it is compulsory that we must take a primary alkyl halide as reactant. So we must take the primary alkyl halide. Means in this case, if the tertiary alkyl halide is taken, so this product formation is not possible. The product formation is possible only when the alkyl halide taken, it is primary. Why so? In case, remember, in case the alkyl halide which is taken is secondary, then we obtains the mixture of ether and alkene, while if we are taking alkyl halide as tertiary, then in this situation only alkene is formed. Why actually? What happens here? If alkyl halide taken is secondary and tertiary, so instead of the substitution reaction, elimination reaction occurs. Why elimination? See, let our alkyl halide is tertiary. Here it is CS3, CS3, and this one is CS3, and here it is Br. Which one is acting as our leaving group? Now the alkoxide is this. Here the sodium ethoxide will furnish the ethoxide ion, and in ethoxide ion is a, here it is acting as nucleophile, but in addition to this nucleophile, this ethoxide ion is itself a very strong base, and as it is a strong base, why it is very strong base? So we may explain this one by taking the conjugate acid base concept here. See, this is an alcohol and will furnish as and produce alkoxide ion and the H plus ion. See, alcohol is a weaker acid. So its conjugate base, this one is conjugate base, will be a strong base. As we know, weaker the acid, stronger will be the base. Stronger the acid, weaker will be the base. So because its conjugate acid, ethoxide ion's conjugate acid is a weak acid, that's why this one is a strong base and will cause, and therefore will remove this. See here, the carbon over which there is a Br, this one is known as alpha, and adjacent carbon, this one is a beta. So because it is a strong base, that's why it will remove this beta hydrogen as H plus ion. So what is going to happen here? This Br minus sits free and this H comes out as H plus and combines to this ethoxide ion, forming alcohol. And the Br minus sets free from here, combines to the Na and will form what? NaBr. Now the remaining species is CH3, here C, CH3. As the two electrons of the CH bond shifted in between the two carbons, here double bond will form. And we will get here alkene as a major product or as a main product. So I think, is it clear? So this was the one of the limitation. The another limitation is the second limitation, while forming alkyl aryl ether, means here this is an example of alkyl aryl ether. So while making this type of ethers, again there is a, see, we may obtain this particular type of ether by treating sodium phenoxide with ethyl bromide. See, it is expected this Na plus comes out with the Br, forming NaBr and ether. See, the another possible reagent or reactants are, this time here I am taking sodium ethoxide and bromobenzene as a reactant, and it is expected that this Br should come out with the Na to get this ether, alkyl aryl ether. But see, here the limitation is that while making this type of alkyl aryl ether, always it is alkyl halide which is treated with sodium phenoxide. Means by this way here alkyl halide is treated with sodium phenoxide. Okay. Aryl halide cannot be taken here. Means we cannot get this alkyl aryl ether using aryl halide and sodium alkoxide. So the reason why? So the reason is that this is because as the aryl halide, or we may call it a haloarine. Haloarenes are very less reactive towards nucleophilic substitution reaction. That's why while forming alkyl aryl ether, it is alkyl halide which is treated with the sodium phenoxide. One more limitation is here. See, the another limitation is, let our ether is this type of ether. This time I am having a diaryl ether, and we want to prepare the diaryl ether using Williamson's synthesis. So one of the reactant must be sodium phenoxide, while another one should be a aryl halide. And it is expected that here we'll get a diaryl ether. But this reaction is not possible because, see, this one of the reactant aryl halide does not give nucleophilic substitution reaction. See, haloarenes are less reactive towards nucleophilic substitution reaction. That's why we are not able to prepare the diaryl ethers using Williamson's synthesis. So these are the limitations of the Williamson synthesis. Okay.